Hello and welcome back to Steve and Data. Today, in this video, we are going to talk about two topics: independence of events in probability and the Bayes theorem. About independence, I should say sometimes we have some events whose occurrence is not dependent on any other event. For example, we flip a coin in the air and get the outcome as head. Then again, we flip the coin, but this time we get the outcome as tail. In both cases, the occurrence of both events is independent of each other. And in this video, I'm going to give you the details of this independence. On the other side, in the previous video about conditional probability, we saw an example that provides the probability of an event given a condition. But after a random experiment generates an outcome, we are naturally interested in the probability that a condition was present given an outcome. In this case, we use the Bayes theorem, which addressed this question in 1763. Okay, that's enough. Let's dive into the video to see what we can get from it about these two important terms. In some cases, the conditional probability of B given A might equal the probability of B. In this special case, knowledge that the outcome of the experiment is in event A does not affect the probability that the outcome is in event B. For example, consider the inspection described in the counting techniques video. 6 parts are selected randomly from a bin of 50 parts. But assume that the selected part is replaced before the next one is selected. The bin contains 3 defective parts and 47 non-defective parts. We are interested in the probability that the second part is defective, given that the first part is defective. In shorthand notation, the requested probability is denoted as this, where A and B denote the events that the first and second parts are defective respectively. Because the first part is replaced prior to selecting the second part, the bin still contains 50 parts, of which 3 are defective. Therefore, the probability of B does not depend on whether or not the first part is defective. That is, the probability of B given A equals 3/50. Also, the probability that both parts are defective is the probability of the intersection of A and B, that equals the probability of B given A times the probability of A, that is 3/50 times 3/50 again, that equals 9/2500. The preceding example illustrates the following conclusions. In the special case that the probability of B given A equals the probability of B, we obtain the probability of the intersection of A and B equals the probability of B given A times the probability of A, that equals the probability of B times the probability of A. And the probability of A given B, as you can see, equals just the probability of A. These conclusions lead to an important definition, which is called the independence of two events, that says two events are independent if any one of the following equivalent statements is true. First, the probability of A given B equals the probability of A. Second, the probability of B given A equals the probability of B. And third, the probability of the intersection of A and B equals the probability of A times the probability of B. The concept of independence is an important relationship between events. A mutually exclusive relationship between two events is based on only the outcomes that compose the events. However, the independence of a relationship depends on the probability model used for the random experiment. Often, independence is assumed to be a part of the random experiment that describes the physical system under study. Now, to understand this definition properly, let's see an example. Consider the inspection described in the last example. But now 6 parts are selected randomly without replacement from a bin of 50 parts. The bin contains 3 defective parts and 47 non-defective parts. Let A and B denote the events that the first and second parts are defective respectively. We suspect that these two events are not independent because the knowledge that the first part is defective suggests that it is less likely that the second part selected is defective. Indeed, the probability of B given A equals 2 over 49. Now, what is the probability of B? Finding the unconditional probability of B takes some work because the possible values of the first selection need to be considered. So, the probability of B equals the probability of B given A times the probability of A plus the probability of B given A prime times the probability of A prime, that is 2 over 49 times 3 over 50 plus 3 over 49 times 47 over 50, that equals 3 over 50. Interestingly, the probability of B without any knowledge of the first part is the same as the probability that the first part selected is defective. Yet, our goal is to assess independence. Because the probability of B given A does not equal the probability of B, these two events are not independent, as we expected. However, there is an issue left. You may have noticed we talked about the independence of two events. But what should we do when we have 3 or more events? Don't worry, we can extend the definition of independence with the following general result. The events E1, E2, E3 up to En are independent if and only if for any subset of these events their intersection equals their multiplications. Now, let's see a cool example about the independence of multiple events. The following circuit operates only if there is a path of functional devices from left to right. The probability that each device functions is shown on the graph. Assume that devices fail independently. We are interested in the probability that the circuit operates. The solution can be obtained from a partition of the graph into 3 columns. Let L denote the event that there is a path of functional devices only through the 3 items on the left. From the independence and based on the previous example, the probability of L equals 1 minus 0.1 cubed. Similarly, let M denote the event that there is a path of functional devices only through the 2 units in the middle. Then the probability of M equals 1 minus 0.05 squared. The probability that there is a path of functional devices only through the 1 unit on the right is simply the probability that the device functions, namely 0.99. Therefore, with the dependence assumptions used again, the solution is 1 minus 0.1 cubed times 1 minus 0.05 squared times 0.99, that equals 0.987. Now let's go to the Bayes theorem. As I mentioned at the beginning of the video, sometimes we might be interested in the probability that a condition was present given an outcome. So to answer this question, we use the Bayes theorem. But before going into the definition, please give attention to this point. Do not let the simplicity of the mathematics conceal the importance. Now, let's see what is the Bayes theorem. From the definition of conditional probability, we have the probability of the intersection of A and B equals the probability of A given B times the probability of B, that is equal to the probability of the intersection of B and A. And it is also equal to the probability of B given A times the probability of A. Now, considering the second and last terms in the preceding expression, now we can write the probability of A given B equals the probability of B given A times the probability of A over the probability of B. And this is a useful result that enables us to solve for the probability of A given B in terms of the probability of B given A. Now, suppose that in semiconductor manufacturing, the probability is 0.1 that a chip subjected to high levels of contamination during manufacturing causes a product failure. The probability is 0.005 that a chip not subjected to high levels of contamination during manufacturing causes a product failure. In a particular production run, 20% of the chips are subject to high levels of contamination, and 80% of the chips are subject to low levels of contamination. Actually, this table summarizes all I have been saying so far. Now, let F denote the event that the product fails, and let H denote the event that the chip is exposed to high levels of contamination. So, the probability of H equals 0.2, the probability of F given H equals 0.1, and based on the total probability rule that says for any events A and B, the probability of B equals the probability of the intersection of B and A plus the probability of the intersection of B and A prime, that is equal to the probability of B given A times the probability of A plus the probability of B given A prime times the probability of A prime. The probability of F equals 0.1 times 0.2 plus 0.005 times 0.8, that equals 0.024. Now we can simply calculate the probability of H given F with the last formula, and this is equal to the probability of F given H times the probability of H over the probability of F, that is equal to 0.1 times 0.2 over 0.024, that equals 0.83. In general, if the probability of B in the denominator of the last equation is written using the total probability rule, we obtain the following general result, which is known as the Bayes theorem. The Bayes theorem says if E1, E2, E3 up to Ek are k mutually exclusive and exhaustive events, and B is any event, the probability of E1 given B equals the probability of B given E1 times the probability of E1 over the probability of B given E1 times the probability of E1 plus the probability of B given E2 times the probability of E2 up to the probability of B given Ek times the probability of Ek. But before wrapping up the video, let's see an example of this theorem. Because a new medical procedure has been shown to be effective in the early detection of an illness, a medical screening of the population is proposed. The probability that the test correctly identifies someone with the illness as positive, which is known as the sensitivity, is 0.99, and the probability that the test correctly identifies someone without the illness as negative, which is known as the specificity, is 0.95. The incidence of the illness in the general population is 0.0001. You take the test and the result is positive. What is the probability that you have the illness? Let D denote the event that you have the illness, and let S denote the event the test signals positive. The probability requested can be denoted as this. The probability that the test correctly signals someone without the illness as negative is 0.95. Consequently, the probability of a positive test without the illness is the probability of S given D prime, that is equal to 0.05. So, from the Bayes theorem, we have the probability of D given S equals the probability of S given D times the probability of D over the probability of S given D times the probability of D plus the probability of S given D prime times the probability of D prime, that is equal to 1 over 506 and it is approximately equal to 0.002. As you can see, the probability that the illness is present given a positive result from the test is only 0.002. Surprisingly, even though the test is effective in the sense that the sensitivity and specificity are both high because the incidence of the illness in the general population is low, the chance is quite small that you actually have the disease even with a positive result. Now, it's time to wrap up the video by reviewing what we have learned so far. First, we saw that sometimes the probability of B given A might equal the probability of B. In this case, we figured out that the outcome of the experiment in event A does not affect the probability of the outcome in event B. Then we conclude that if two events have this relationship with each other, we would call them independent. But generally, we call multiple events independent provided that their intersection equals their multiplications. Then we became familiar with the Bayes theorem that says if E1, E2, E3 up to Ek are k mutually exclusive and exhaustive events and B is any event, then the probability of E1 given B equals the probability of B given E1 times the probability of E1 over the probability of B given E1 times the probability of E1 up to the probability of B given Ek times the probability of Ek. And that is done. Congratulations! Now you know some information about the independence of events and the Bayes theorem, and you are able to solve the really complicated problems with the help of them. At last, if you like this video, please hit that like button, and if you are interested in probability, statistics, and data science topics, please consider subscribing to this channel. By the way, if you have a question about these subjects and anything related to the fields I mentioned, comment it down in the comment section. I will answer them as soon as possible. I hope this video helps you a lot, and until the next video, happy learning!